Hello everybody and welcome to this A-level chemistry video, which is an introduction to the amount of substance topic. And in this video we're going to look at the relative atomic and molecular masses, the mole and the Avogadro constant. So we'll start by defining relative atomic mass and relative molecular mass. Then we'll look at how you can calculate relative molecular mass. And then we will explain what the Avogadro constant is and explore its connection to the mole. Then we'll look at some moles calculations using moles mass and relative molecular mass. Then we'll look at moles of solutions and how we use those concentration calculations. And then we'll finish with the challenge of looking at how we can do calculations using the Avogadro constant. The actual mass of any atom or molecule is actually too tiny to find by weighing, so instead the masses of atoms are compared and relative masses are used, and that's why we get the term relative atomic mass, which has got the symbol Ar. In the past, defining relative atomic mass, we used hydrogen as the lightest element with a mass of 1, and so oxygen, which is 16 times heavier, had a relative atomic mass of 16. We've moved on now to use the isotope carbon-12 as our reference because the mass spectrometer has allowed us to measure the individual isotopes' masses extremely accurately, and we found that 1/12 of the relative atomic mass of carbon-12 is a value of exactly 1. And so the carbon-12 standard is now the accepted definition by all chemists throughout the world for relative atomic mass, and it's here. And so relative atomic mass is the average mass of one atom of an element divided by 1/12 of the mass of one atom of carbon-12. Or, if you prefer, you can remember it as a sentence. The relative atomic mass, Ar, is the average mass of one atom of an element compared to 1/12 of the mass of a carbon-12 atom. So really very similar. And in the same way, we can handle molecules by comparing the mass of one molecule to that of an atom of carbon-12. And so the relative molecular mass, Mr, is defined as being the average mass of one molecule divided by 1/12 of the mass of a carbon-12 atom, or the average mass of one molecule compared to the mass of one atom of carbon-12. And these are definitions that you need to remember, both of these. You could be asked to recall them in an exam for 1 or possibly even 2 marks. Calculating Mr is exactly the same as you used to do at GCSE in principle. So you find the relative molecular mass by adding up the relative atomic masses of any of the atoms present in the molecule, and you find this out from using the formula. So H2O has got obviously 2 hydrogen atoms in and 1 oxygen. And so each hydrogen has got a relative atomic mass of 1.0. That's probably the only difference between A-level and GCSE. We go to an extra decimal point for all of the atoms. And so hydrogen is 1.0, but there's 2 of them. And then oxygen is 16.0. So we add together that 1.0, 1.0 and 16.0 and get an answer of 18.0. And it's vital that you include that 0 at the end. One last example, methane, CH4, has got 1 carbon, which is 12.0, and 4 hydrogens, so that all adds up together to get 16.0. The only way that this can get complicated is if you've got a bracket. Remember, a bracket means you've got multiples of anything inside it, so in this case we've got magnesium hydroxide, so we've got 1 magnesium atom and we've got oxygen and hydrogen once inside the brackets, but that 2 means we've got 2 of everything inside the brackets, so we've got the relative atomic mass of 1 magnesium, add 2 lots of that oxygen mass and 2 lots of the hydrogen mass, which gives us an answer to 1 decimal point here. I want to quickly just make one distinction between relative molecular mass and relative formula mass. Some people think that you can use these interchangeably, but that's actually not the case. Relative molecular mass, unsurprisingly, refers to molecules, whereas relative formula mass refers to things that maybe aren't molecules, and specifically really what we mean is ionic compounds. So they don't exist as molecules. But what's a little bit confusing, well, very confusing really, is that it also has the symbol Mr. But the good news is the calculation is exactly the same. So for instance, like calcium fluoride, which has got 1 calcium and 2 fluorines, it's 40.1 for the calcium, 19.0 for each of the 2 fluorines. That gives us an MR value of 78.1. Don't forget, 1 decimal point for MR values that you've calculated should be easy to remember because they give you the AR data, the relative atomic mass data, to 1 decimal point. And so you should always report your final answer to the same amount of precision that you're given in the question. And in fact, it's really important that you realise that calculated results can only be reported to the limits of the least accurate measurement. And so what that means is, if 2 pieces of data you've been given are to 3 significant figures, but a third piece is only to 2 significant figures, your final answer should only be to 2 significant figures. Now, 1 atom of any element is too small to see, of course, and it's also too small to weigh by itself. So to count atoms, we weigh large numbers of them, which is the same as they do in banks when they're weighing coins and banknotes. They don't count them all sometimes, they actually just weigh them and know how much they must have based on the weight. And that's the same with atoms. So for instance, helium, which has got a relative atomic mass of 4, is 4 times heavier than an atom of hydrogen. And so what that means is, if you had the same mass of each of them, helium and hydrogen atoms, we would have 4 times as many hydrogen atoms. And in the same way, carbon is 12 and helium is 4. So if we've got the same mass of each of them, we will have 3 times as many atoms of helium. And we can apply the same logic with molecules, and so carbon dioxide is 44 and helium is 4, and so if we have the same mass of carbon dioxide and helium, we would have 11 times the number of particles of helium than we have of carbon dioxide because of those masses. Now, if you weigh out the relative molecular mass or relative formula mass of, or MR, of a compound in grams, you have the same number of entities in 2 of these. And so this number is given a constant, and that's the Avogadro constant. And this is a massive number, and it's 6.022 times 10 to the 23. So approximately 602,000 million. Massive number. And this number is called the Avogadro constant. And the Avogadro constant, or Avogadro number sometimes it's called, is the number of atoms in 12 grams of carbon-12. And so it's therefore the number of atoms in 4 grams of helium, because they are the same number. And the amount of substance that contains Avogadro's number, worth of particles or entities, is called a mole. And an entity means an electron, an ion, a molecule, an atom, or the simplest formula of an ionic compound such as NaCl. We would have a mole. So in 1 mole of carbon, we've got 6.022 times 10 to the 23 particles, and in 1 mole of oxygen molecules, we've got this many molecules as well. So a mole is defined as this number of entities, Avogadro's number's worth of entities. The good news is you're not going to be expected to remember Avogadro's number. If you need to work with it, you'll be given it in an exam. Now, in terms of the power of this, there's one more amazing thing, which is that the relative atomic mass of any element in grams contains precisely 1 mole of atoms. And, by extension, the relative molecular mass, or formula mass, depending on what you're using, of a substance in grams contains 1 mole of entities. And so you can have a mole of ions or a mole of electrons as well. And any of those quantities will always have 6.022 times 10 to the 23 entities. And so for oxygen atoms with a relative atomic mass of 16.0, the mass of 1 mole of oxygen is 16.0 grams. And this is a good point to mention that relative molecular mass or atomic mass have got some units. And you don't need them at A-level chemistry, but it's actually quite helpful, I think, to help you remember it. And that is grams per mole. And so 16.0 grams per mole of oxygen atoms. And that's quite helpful. And so oxygen molecules, O2, which has got 2 oxygens added together, the relative molecular mass is 32.0 grams per mole. So it's really obvious then that the mass of 1 mole of oxygen molecules is going to be 32.0 grams. And so the mass of 2 moles of oxygen will be 64.0 grams, twice as many particles, twice the mass. If you want to calculate the number of moles present in a particular mass of a particular substance, you need to know the substance's formula, and if you do that, you can work out what the mass of 1 mole of that substance is, or its MR. And the calculation to work out how many moles you've got is the number of moles is equal to the mass in grams divided by the mass of 1 mole, whether that is AR or MR. So we can write that in more shorthand form as N for moles equals mass M divided by mass of 1 mole, which is AR, or N equals M over MR as well, depending on which it is that you're calculating. Now, when you're working with this equation, you won't always be calculating moles, you might be calculating one of the other two. I prefer to rearrange this equation using algebra. So if we take it in its form that we've got here and we multiply both sides by relative molecular mass, we get mass equals MR times moles, or mass equals Mr. Moles. Alternatively, we could multiply by MR and then divide by moles, and then we get the rearranged form of MR equals mass divided by moles. So that's the algebra method. Other people prefer the formula triangle, which has got mass on the top and moles times MR on the bottom, and then you cover up what you're looking for, and what's left is the calculation that you have to do. So there really is no better way of doing it. It is what is your preference out of those two methods. We'll just take a look at one question that involves rearranging that formula. What is the MR of 0.34 moles of a substance if it's got a mass of 15.64 grams? So we know M and we know the moles, and so moles equals mass divided by MR rearranges that to MR equals mass divided by moles, and so mass is 15.64 and moles is 0.34, and when we divide that number we get an answer of 46.0 grams per mole, but I'll put that in brackets because you don't need those units at A level. It's just helpful. Now, the concept of moles isn't just confined to things that are pure, solids, liquids and gases that you know the masses of. You can also work out moles in solution. Now remember that a solution is when a solute is dissolved inside a solvent, and so if you know the mass of solute and the volume of the solvent that you've dissolved it in to make the solution, you can work out a concentration in grams per cubic centimetre, or most commonly grams per cubic decimetre. And so concentrations can have this unit, grams per cubic decimetre, such as in this calculation here, where if we've got 2.34 grams of sodium chloride, that has got an MR of 58.5, that is 0.04 moles. If we're putting this into 500 cubic centimetres, so 0.5 cubic decimetres, then that is a concentration of 0.08 moles per cubic decimetre, or which has the same concentration as 4.68 grams per cubic decimetre. Now, most concentrations that you'll be given in an exam will be moles per cubic decimetre, mol dm minus 3. And so that's going to be the units of concentration. And so what that means is the units of volume that you're working with will normally need to be in dm cubed. And so to calculate the number of moles of a solution, it's moles, N, equals concentration, C, times by volume, V. So N equals C times by V. That's provided the V is in dm cubed. So remember, there are 1000 cm cubed in 1 dm cubed, and so we need to divide the volume in centimetres cubed by 1000 to get our decimetre cubed volume. And I know people like to have formula triangles to rearrange this equation. So N is moles, and that's on the top of the triangle, and concentration times by volume is on the bottom. So you cover up the bit that you're interested in, and what you're left with is the calculation that you do. Two quick questions here for the application of that. So how many moles are there in 30.0 centimetres cubed of solution with a concentration of 0.2 moles per decimetre cubed? So the first thing that we need to do is turn that volume into decimeters cubed by dividing by 1000. So that is 0.030 cubic decimeters, and our concentration is exactly the same, 0.20, no conversion needed there. So moles is concentration times by volume, which is 0.20 times by our volume, 0.03, which gives us an answer of 6 times 10 to the minus 3 moles. Then in the second question, what is the concentration if 2 moles are placed in 800 cubic centimetres of solvent? So again, the first thing we need to do is turn that into dm cubed, divide that by 1000, and we get 0.8 on there. Moles is exactly the same. So N equals C times by V, so therefore C equals N divided by V, so we need to do 2 divided by 0.8, and that gives us an answer of 2.5 moles per cubic decimeter. Now, you could, in an exam, be asked to use the Avogadro constant in some form in a calculation. And the first one that you might be asked to do, actually, is to do a calculation that requires knowledge of the Avogadro constant, but you don't actually need to use it. So, for instance, in this question here, which of these two has got the greatest number of atoms? Which contains the greatest number of atoms, 6 grams of carbon or 89.00 grams of gold? Now, we need to know what the relative atomic masses of each of these is before we can do this calculation. And so the relative atomic mass of carbon is 12, so moles equals mass 6.00 divided by the MR, which is 12.0. And so that is 0.50 moles. And then for gold, moles equals mass divided by relative formula mass, which is 197.0, which gives us 0.45 moles. So the answer here is carbon will contain the greatest number of atoms because it's got a greater number of moles. To find out precisely how many atoms there are, we would multiply this number of moles by Avogadro's number, but that's not what we've actually been asked to do here, so there is no requirement to do this, but that's how we would find the actual number of atoms. This next one looks like it's exactly the same, but it's actually a little bit trickier. And the reason it's trickier is because we've got water here, which is a molecule, H2O. And so moles equals mass 10.8 divided by the MR of water, which is 18.0, which gives us 0.6 moles. Now this is moles of H2O. And in H2O there are 3 atoms. So moles of atoms is therefore going to be 1.8 moles of atoms because there are 3 atoms for each molecule of water. So there might be 6.022 times 10 to the 23 molecules of water, but there will be 3 times that many atoms because each molecule of water has got 3 atoms. And so for helium then, moles equals 4.8 divided by 4, the AR of helium, which gives us 1.2 moles. And so now we can see that even though the number of moles of a specific entity was smaller for water, when we multiply it by 3 for the 3 atoms that are present per molecule, we get a bigger number, and so the answer is there's more atoms in 10.8 grams of water. So a slightly different form here, so how many atoms are there in 57.0 grams of ammonia? The first thing that we need to do in this approach is work out what the MR of ammonia is. So 14.0 plus 3 lots of 1.0 gives us 17.0 grams per mole for ammonia. And then the moles, therefore, is 57.0, the mass, divided by the MR, which is 17.0. And that gives us an answer of 3.35 moles. 3 significant figures. And then Avogadro's number is 6.022 times 10 to the 23. And so the number of molecules is Avogadro's number times by the number of moles. And that tells us how many molecules of ammonia we've got. And then we need to multiply that number by 4 because there are 4 atoms per molecule, because there's 1 nitrogen and there are 3 hydrogen, and so that makes 4. And so 3.35 moles multiplied by Avogadro's number gives us a huge number of 2.02 times 10 to the 24 molecules, and then when we multiply that number by 4, we're going to, of course, get 8.08 times 10 to the 24 molecules. Just note for your kind of mathematical comfort that the only digits that change when you multiply this number by 4 is the 2.02. That's been multiplied by 4. That's been multiplied by 4. The standard form doesn't change when you're multiplying a number by 4. You can just look at what precedes the standard form and multiply that by 4. Moving on to a different type of question using the Avogadro constant, what is the mass of one atom of a particular substance to 3 significant figures? Well, first up we've got carbon here. Now the relative atomic mass of carbon is 12.0, and what that means is 1 mole of atoms has got a mass of 12.0 grams, and so 6.022 times 10 to the 23 atoms of carbon has got a mass of 12.0 grams. And so to find out what the mass is of 1 atom of carbon, we need to divide both sides of this equation by Avogadro's number, which is sometimes given the symbol L, by the way, just for ease. So we're dividing both sides by 6.022 times 10 to the 23, and when you divide the left-hand side by that number, you get 1, because you're effectively dividing it by itself. And when we divide the right-hand side by that number, we get a very small number, 1.9926 times 10 to the minus 23 grams, because remember that the mass of 1 mole's worth of atoms is in grams, so when you divide by Avogadro's number, it will still be in grams as well. And then we need to get that to 3 significant figures, and the first, second, third, fourth significant figure is a 2, so actually we're allowed to just get rid of those 2 digits because we don't need to round that 9 upwards. So 1.99 times 10 to the minus 23 grams is the mass for carbon. Magnesium, doing these ones faster, the AR is 24.3, so that is the mass of 1 mole. So 1 mole equals 24.3 grams. So we divide both sides by Avogadro's number, and we get a mass of magnesium of 4.035 times 10 to the minus 23 grams, which then we need to round to 3 significant figures to 4.04 times 10 to the minus 23 grams. So remember, we're dividing by Avogadro's number for the mass. And so for aluminium, we've got 27.0 is the relative atomic mass. We divide it by Avogadro's number, 6.022 times 10 to the 23, and we get a value of 4.4835 times 10 to the 23 grams, which to 3 significant figures just becomes 4.48 times 10 to the minus 23. But this time the question was a little bit cheeky because they asked us for the mass in kilograms, so we then just need to divide by 1,000 to get 4.48 times 10 to the minus 26 kg. And so the mass of 1 atom is the relative atomic mass divided by Avogadro's number. That's how you calculate the mass of 1 atom of anything. Obviously there are other types of question they could ask you about this, but they're all variations on this theme. So I think we will end the video there, and I will see you again soon for more amount of substance. Thanks for listening.